Um, Today we're looking at lesson 3 in Unit 11, and we're going to look at how to write and balance half reactions for redox reactions. Okay, so here's the agenda for today, and you'll notice I'm going to do a quick reteach of oxidation numbers just because I didn't like how the last lesson came out. This is not based on any feedback, it's just my own personal feeling about how the lesson came out. So I'm going to do a quick reteach about that. Hopefully it helps since we, kind of need it for the rest of this lesson anyway. So maybe it's just a review for you. Okay, now we'll do now, look at writing, balancing, check for understanding. Pretty straightforward. Okay, so here it is. Now, I gave you a lot of rules for oxidation numbers in the last video, but realistically, I mean, you have this reference table which lists a lot of them. So the rules aren't wrong that I gave you. It just may be unnecessary for you to know those. Okay, so I'm simplifying them a little bit. So free elements, always zero. That's still a rule. Okay, if it's an element all by itself, it's just zero. And that includes those diatomic, right? So O2 is still an element all by itself, and that gets an oxidation number or oxidation state of zero. For the rest, use your periodic table, right? All the oxidation numbers are listed in the upper right-hand corner. So remember, I gave you rules like group 1, they're all +1. Well, that's what your periodic table says. Now, you don't have to memorize that because they're all right here. Group 2, they're all +2. Oxygen is always -2. Fluorine is always -1. Okay, so you don't have to memorize those. They're on your table. Just use the table. Because there are some that, like boron is always +3. Aluminum is always +3. It's no sense in making rules for every element, right? So just use this. That's why it's here. I will say one thing, though. Remember that, look at hydrogen, right? It can be +1 or -1. For our purposes, it's always going to be +1. All right, so you can ignore that -1 there. It does, realistically, it does have a -1 oxidation state at times in some compounds, but most of the time it's a +1. And for us, it'll always be +1. Yeah, so there's that. Okay, that simplifies that a little bit. A new rule I added, but I did talk about it, but I didn't have it in there last time, was that elements in ionic compounds, their oxidation state is the same as the charge of their ions. So you might have to do kind of reverse crossover method to see what the charges are, but that's how you find the oxidation state if you have an ionic compound that has two elements that could have multiple oxidation states. So you can't just look them up, right? And that kind of ties into the last one here. If you have elements where you don't know the oxidation state because something like nitrogen, right? Look at all those oxidation states. Could be any one of those. When you have something like nitrogen, you have to kind of save it for last, and then you add up all the oxidation states, and then it should equal the total charge of the compound, which is usually zero, right? Not always, but like for all of these examples, right, there's no charge in the top right-hand corner. They're all zero. So you make sure the oxidation states all add up to equal zero. So you have to do a little bit of algebra for the elements where you don't have a very straightforward one like nitrogen. Okay. So let me do some quick examples, right? So, right, element all by itself, oxidation state is zero. Okay, here's an ionic compound. We have calcium and chlorine. I'm looking, well, look at that. Calcium is always +2. That one's easy. +2, because it tells me that. Chlorine, not so simple, right? Chlorine can be +1, -1, +5, +7. Okay, but here we know that it all has to add up to zero, which is the charge. So there's two chlorines, and I have to balance out this +2 to get to zero. So that means each of them has to be -1. Okay. Over here, right, we got three elements. So oxygen, if you remember one of the rules from last time, or we could look it up, always -2. Okay, -2. Copper could be +1 or +2, so we don't know for sure. But look at rule 3. This is an ionic compound. So copper is going to have the same oxidation state as the charge in this ionic compound. Now, NO3 is a polyatomic ion, and if you look in your table, let's see here, let's go up, NO3, nitrate, right here, has a -1 charge. Okay, let's go back to my periodic table. So if this is -1 and there's two of them, copper, to balance it out, notice how there's no charge on the whole compound, to balance it out has to be +2. That's how we figure this one out, okay? Because on the periodic table, it said it could be +1 or +2, but it's going to have the charge, or the oxidation state is going to be the same as the charge as it is in the compound. All right? And we can use that polyatomic ion trick again, because since this NO3, we could ignore this 2 for now, since this NO3 has a charge of -1, right, the oxygens, the 3 oxygens and the nitrogen all have to add up to -1, okay? So 3 times -2 is -6. How do I get to -1? Well, I have to add 5. So nitrogen is +5. And you will see that it does work, right, if I include the 2. Okay, so, right, technically there's 3 times 2, there's 6 oxygens here, right, for a total of -12. And there's 2 nitrogens for a total of +10, which makes -2 total for this, which balances out by the +2, okay? So it will work out. When I say ignore the 2, I mean you can ignore it just to come up with the oxidation states, but it all still works out if you use it. So it's either way. All right, so hopefully that makes it a little bit simpler, right? Rely more on the periodic table than memorizing, okay? And just be careful of hydrogen. Hydrogen's always +1. All right. So for do now, here it is. Okay, I'm going to have you assign oxidation numbers and tell me what element is oxidized, what's reduced. And then a little bit of extra down here, 2 and 3 should be easy based on what I've given you. So go ahead and pause, try that out, and then unpause me. Okay, so oxidation numbers, right? I'm going to start with, well, didn't we just look at these in the last problem? I think I just looked at this one, right? So hopefully you noticed that, and this is a -2. This is a +5, right? And the reason I'm just doing this really fast is we literally just did this in the reteach in the last slide. This is a +2. Okay, element all by itself, 0. Element all by itself, 0. Okay, now we got to look at this one though. Oxygen always -2. Look it up in the periodic table. Ag, look it up. Boom, always +1. Super helpful when it's only one option. That means nitrogen's the only one that's left, and we know nitrogen's a pain in the butt because it can be any of those. So, so we got to do a little math, right? -2 times 3 is -6, +1 is -5. How do I balance that out? Notice there's no charge in the top right, so it has to equal 0. How do I balance out -5? Well, +5. Okay, so we got our oxidation states. Now I also asked you which element is oxidized and which is reduced. Now, notice copper goes from 0 to +2, right? Which means it must be losing electrons, which is oxidized. OX for oxidized, okay? Whereas silver here, and notice, right, nitrogen doesn't change, oxygen doesn't change, so we ignore them. Silver, Ag, goes from +1, oops, okay, to 0. Literally, it's being reduced. The oxidation state is being reduced. So that's reduction. R-E-D for reduction, right? You notice redox, right? Okay, hopefully you got that. And then a little bonus here, right? This is actually technically new. And it's just kind of a terminology thing. The reducing agent is always the element that gets oxidized, okay? So the reducing agent is copper, right? Because it gets oxidized. It's opposite, right? And then the oxidizing agent is the element that gets reduced. So silver got reduced. Silver is the oxidizing agent. Okay. So it's just kind of backwards from. If it gets reduced, it's if it gets reduced, it's the oxidizing agent. If it gets oxidized, it's the reducing agent. All right. Cool. So writing half reactions. So we know that in a redox reaction, right, one half is a reduction and the other half is oxidation. They always occur together. That's why it's called redox. Each process can be written separately, and we include the electrons in half reactions, okay? So let's look at this equation here. We always start by assigning the oxidation numbers. Now, I'm not really great with the pen, so I'm going to go ahead and switch to, oh, and I forgot to turn my camera on. So give me 1 second here. See if you can assign those oxidation numbers while I get prepared. Oh, just adding time onto this. Okay, here we go. Maybe. All right, cool. So, and again, there's our equation, so I'm going to write it down. We got AgCl plus Cu going to CuCl2 and Ag. Okay, so we start by assigning oxidation numbers, then we write reduction and oxidation as separate, including the electrons. So here's what that looks like. So oxidation numbers. Copper 0 by itself, silver 0 by itself. Ag, if you look at the periodic table, it's +1, which means the chlorine here is -1. Copper, chlorine, this is one of those ones where you have to recognize it's ionic, and it has the charges. The charges of the ions in the ionic compound are the same as the oxidation state. So chlorine here is going to be -1, and that means copper is going to be +2. Okay, I know I'm going kind of fast, but this is technically a review here. Okay, so now we're looking at, right, oxidation and reduction. Well, copper, right, copper goes from 0 to +2. That means it lost electrons. That means oxidized. Silver goes from +1 to 0, right, which means it gained electrons and got reduced. Okay, so now we can write each of these reactions separately. Let's start with oxidation. So we start off with, and this is oxidation, okay, we start off with copper, Cu, with a 0 charge, okay. We said it's oxidized, so it must be losing electrons, right? If you're losing something, it's going to come out on the product side. So we draw the arrow, and then copper becomes, right, that 2+ charge. So Cu +2. Okay, really it should be 2+ for the charge, but whatever. Which means that it must have lost 2 electrons. Okay, right? Notice that the charge is balanced. 0 charge on the left side of the arrow, 2+, 2- on the right for a total of 0. Okay, now let's write our reduction half reaction, which is here, the silver. So we started with Ag+. And we said reduction is the gain of electrons, so plus. How do we get, and right, so we'll do the electrons last. So it's going to add some number of electrons and bring us to Ag0, no charge, right? So how do I get from +1 to 0? How many electrons? Well, just 1, right? So notice how we have, these are half reactions. Here's the oxidation half, right? Copper losing 2 electrons, right? In oxidation, the electrons will always be on the product side. Reduction is the gain of electrons. If you're gaining something, right, it's always going to be on the reactant side. Okay? So here we have the reduction half reaction. And that's it. That's how you write half reactions for redox. Okay? Now, that's just writing them. Now you'll notice maybe something weird here, right? There's 2 electrons involved here, only 1 here. That doesn't seem right. Well, it's not, because we have to balance them. So, in a complete reaction, the number of electrons lost must be equal to the number of electrons gained, right? So, the number of electrons used in the reduction must equal the number of electrons produced in the oxidation, right? So kind of saying the same thing. So what we can do is we can take an entire half reaction and multiply it by a number so that the electrons are equal on each side. So let's look at the equation we just worked on, right? So right, if you notice, there's 2 electrons involved in this reaction, but only 1 electron involved in this reaction, right? Here's the simple way to do it. If I just multiply this whole reaction by 2, right, it'll balance them out. But I have to put a 2 in front of everything, or multiply everything by 2, right? So this gets multiplied by 2, this gets multiplied by 2, this gets multiplied by 2. And now the electrons are equal. There's 2 electrons here, there's 2 electrons there. That's good, okay? Now when we rewrite the whole equation, I'm not even going to rewrite it. You know what? I'm going to change the coefficients up here. So I made this Ag a 2. That means the compound with the silver has to get a 2. I can ignore the electrons for now. And then the silver on the product side, whatever compound that is, in this case it's just all by itself, also gets a 2. Boom. And if you notice, the equation's balanced. 2 silvers, 1 chlorine, 2 chlorines, 2 chlorines. one copper, one copper. Okay? So that's how you do that. Okay, so you write each of the half reactions, then you multiply so that there's equal number of electrons in each of the half reactions, and then whatever you did, whatever you had to do to get there, change it in the original equation. Okay? All right. Wrong way. So, time for you to try one. Okay? So you're going to write the half reaction just like I just did, and then balance the equation like I just did. And notice you already assigned oxidation numbers to some of these in the do now. I think all of these. This is the exact equation I gave you. Yeah, so there you get a little head start. So go ahead, try that, pause me, and then unpause, and I will go through it. Okay, so I'm going to write this guy down. We got silver nitrate, right, AgNO3 plus copper goes to copper nitrate, CuNO3 2 plus silver. Right, you might recognize this. We'll throw back here. This is a single replacement reaction, right? Okay, so let's do this. Here's our equation. We assign oxidation numbers. It should have been easy because you did it in the do now. Element by itself, 0. Element by itself, 0. Oxygen is -2. This copper was a +2. Nitrogen was +5 here. -2 plus 5, and that was a +1. Okay, hopefully you got those oxidation numbers. Now we have to figure out what's oxidized, what's reduced. Looks like copper here. I think we did this in the do now as well, didn't we? Copper goes from 0 to +2, meaning it lost 2 electrons. If you're losing electrons, you are oxidized. Whereas silver goes from +1 to 0, which means literally it's getting reduced, right? The oxidation state is getting reduced. Cool. So we know what's oxidized, we know what's reduced. Now we write our half reactions. So here's the oxidation half reaction. That's here. We start off with copper with no charge, right? Oxidation is the loss of electrons, so the electron should be on the product side. So I can draw my arrow. Copper is going to become copper 2+, and I'll write the charge the correct way this time. Right? Which means if it went from 0 to 2+, it must have lost 2 electrons. Okay? And then we have our reduction half reaction, which is here. We have silver starting off with a plus charge, right? If it's going from +1 down to 0, it's only gaining 1 electron, right? In reduction, we see the electron is on the reactant side. So silver gains that electron and becomes silver, with an oxidation state of 0. Okay, and then, right, those are our half reactions. Then we have to make sure the electrons are equal. So I see 2 here, I see 1 here. Okay, this looks really similar to the last one, right? It's a different equation, but it's almost identical in terms of the oxidation and reduction half reactions. It is identical. Look at that. Okay, so I'm going to put 2's, right? I'm going to multiply this whole equation by 2 so that we get this 2 electrons, right? That's why we're doing it, to make sure the electrons match up. Okay, but now I want to go back and put in my coefficients, right, wherever these pop up. So my silver is here, this whole thing gets a 2, right? And then the other silver is here, that whole thing gets a 2. All right, and we'll check in terms of atoms, right? Because we're just basing this off electrons, right? Which is a great way to balance, it works. So we have 2 silvers here, 2 silvers here. We have 2 nitrogens. Look at 2 nitrogens, right? It makes this a lot simpler, actually. And we have 6 oxygens here. 2 times 3 is 6. 6 oxygens. Okay, 1 copper, 1 copper. Cool, balanced. All right, so rewatch if you want me to go through that again. Real quick, though, I do want to say one thing about the homework, right? A little homework hint, just the way the homework is phrased. Remember that the coefficients in a balanced chemical equation represent the mole ratios, okay? It's not just the number of elements or compounds in one reaction, but it's also the number of moles, because moles are just a number of things, like a dozen, okay? So if I asked you, in this equation that we just balanced, right, how many moles of electrons are lost by copper? Look, Look at the half reaction. How many moles? 2 moles are lost by copper. Okay, that's the answer to that question. You're looking at the coefficient when it asks for number of moles. Okay, so you should respond 2 to that. And that's not obvious in this equation, and that's not obvious in, not super obvious in this equation, but in the half reaction, it's very obvious. So that's where you want to look. Okay, you want to look at the coefficient in front of the number of electrons. All right, so hopefully that gives you a little hint with the homework, because I think a lot of them are phrased like that. Okay, so hopefully that cleared up oxidation numbers if that was confusing from the last lesson, and good luck on the homework.